On page 16 in your notes, I mentioned that I would finish filling out the derivation of the formulas for the mean and the standard deviation of the sampling distribution of sample means. It's not something you actually need to know, but it is kind of nice to not only see the application of our linear transformations and our combination of random variables from last unit. It's kind of nice that it's not just some mysterious formula that you're not smart enough to understand. Like, we can visually see how this is created. So it says choose an SRS of size n from a population. There's some quantitative variable on each individual of the sample. So these individual measurements are x sub 1, x sub 2, all the way through x sub n, because there are n of them, whatever the sample size is. If the population is relatively large, if the sample is small for the large population, basically, we could think of these as independent random variables, each with a mean and a standard deviation. So what this means is if I want to find my average, I just need to add up all these observations and divide by however many there are, which means I can think of this, I'm going to leave a space, as x sub 1 plus x sub 2 plus x sub 3 plus x sub 4 plus x sub 5, all the way through x sub however many there are. If I add them up and divide by n, and I'm going to change that as multiplying by 1 over n. Dividing by 2 is the same thing as multiplying by a half, so I'm just going to multiply by 1 over n. So that's going to be important because I'm taking the sum of my random variables and I'm multiplying it by a constant. We're going to apply both of those things. So I'm going to just let this sum, this x1, x2, x, whatever, I'm going to let it just be represented by t. So that the average that I just wrote out is this constant times my random variable t. My rules for addition, for my means, my variances, and whatnot, I've told you before, you're allowed to add means. So if t is the sum of all these x's, then the average of t is the average of my first x plus the average of my second x plus the average of my third and my fourth and my fifth and my nth x. But it was said at the very beginning that they all have mu for their mean, for their average. So there'll be mu plus a second mu plus a third plus a fourth plus a fifth plus an nth mu. So there would be n of those mu's. I could do the same thing for my variances because you're allowed to add variances as well. You can't add standard deviations, but you can add variances. So I'll take the variances, my variance for x sub 1 plus my variance for x sub 2 all the way to the variance of x sub n. Now again, those were all stated to just be sigmas. So I will just have a string of sigmas summed together. Specifically, again, there are n of those, I wrote sigma, didn't I? These are variances. I will have n of those variances. If they have a standard deviation of sigma, then they would have a variance of sigma squared. My apologies. But since I now know the variance of t, I can find the standard deviation of t by just square rooting it. So I will take the square root of n sigma squareds. And I can simplify that. I can't simplify the square root of just a number that doesn't have a pair, but the square root of sigma squared is just sigma. They cancel each other out. So these are in terms of t. But remember, t is just a constant multiple of my random variable. So, x bar is a constant multiple of t. So what I'm going to do now is just say, well, if I'm multiplying it by a constant, I can just take my mean times that constant. So this is the constant times the mean of t. So this is just my linear transformation rules. So mean of t I already found was n of those mu's, so I'll have 1 over n times n of those mu's. So we can mathematically, algebraically show why the mean of our sampling distribution of x bars is just the population average. Not only because it's an unbiased estimator, but because mathematically, using our rules for random variables, we can show that it's mu. Similarly, I can take that constant times my standard deviation of t, which I already found was sigma root n. So, how am I going to write this one? I'm trying to think of what I want to show you for this one. So the first thing I'm going to do is I'm just going to put this all over n. I'm just going to kind of combine them. And that's not true. I'm actually going to pull sigma off to the front because I would like to get these n's in some way simplified because that just is odd. It's like if I had the square root of, well, that's not true. I would just like to combine them because they're variables. So what I'm going to do is I'm going to put them both in a square root. The only way to put a number that's not square rooted into a square root is by squaring it, which means that denominator, I'm going to square it and also square root it. So I'm not technically changing it. It still simplifies to n, but now since they're both under a radical, I can put them both under one radical. Which means I can simplify that to 1 over n. I could take the square root of 1 and the square root of n. Square root of 1 is just a 1, which is why it's sigma over root n. So not a super intuitive process of figuring that out, especially if your algebraic simplification skills are a little bit rusty. But I did want to show it to you rather than just saying, hey, here's a magic formula, trust me, it works. Here's the algebraic mathematical reason why it works that you don't actually need to